So in the last lecture, we learned that if you have irrotational inviscid flow, you can use potential flow theory, and that if you start with irrotational inviscid flow, then you'll always have irrotational flow because if as long as there's no viscosity, you can't have any, you won't have any generation of vorticity, therefore you won't have any rotation in the flow. So if you can have a flow where that's a reasonable approximation, you can use this technique. So we'll go ahead and show how people do use this technique. Remember, the potential function is such that when you take the gradient of the potential function, you get back the velocity vector. So here's the potential function. We take its gradient, we get d phi dx, d phi dy, d phi dz. It's the three elements of that vector, and that those correspond to u, v, and w. So if we look at that in the case of incompressible flow, we can write down the conservation of mass equation for incompressible flow. And the conservation of mass equation for incompressible flow, du dx plus dv dy plus dw dz is equal to 0. So now we're going to plug in, this for u, this for v, and this for w, because that's what they are, and we'll see what this equation gives us. And what it gives us is d by dx of d phi dx plus d by dy of d phi dy plus d by dz of d phi dz is equal to 0. So for conservation of mass to hold true, that has to be true. That's just saying that d squared phi dx squared plus d squared phi dy squared plus d squared phi dz squared is all equal to 0. So that is a very famous equation. It's usually written in more simpler terms, just like this. Del squared phi is equal to 0. That's the Laplace equation. So you may or may not have seen the Laplace equation yet. You're going to see it very soon in EGR 301 if you have not seen it already. It is a very famous partial differential equation that has been solved many, many times. And long before people really applied it to fluids, people had already been studying the Laplace equation. So that made it a very powerful finding that you could use solutions to the Laplace equation to study certain fluid flows. Remember, this Laplace equation for potential flow can only be used for inviscid, irrotational, incompressible flow. So del squared phi equals 0. Inviscid, so you have to assume there's no viscosity. Of course, that's never ever really true. Irrotational, that is true, but if we have irrotational flow and there is viscosity, we might get some rotation. And incompressible flow, which is a very good approximation for many flows. So while that's obviously not really true, it's a good one. But in many flows for many years could be treated as inviscid, irrotational, incompressible, and therefore people could use this type of solution. The best thing about this was that you could solve this without a computer. So this was very, very powerful tool that people were able to use before people invented the computer. It is a linear PDE. So I'll write that. This is a linear PDE. The reason that's important is because it means that you can combine solutions. So what that means is, therefore, if phi sub 1 is a solution and phi sub 2 is a solution, then phi 1 plus phi 2 is a solution. That's true of any linear PDE. So if you wanted to solve a complicated problem, and this is what people did back in the day, you would solve a fairly simple problem that was related to the problem you're trying to solve. Then you try to solve another simple problem to generate another solution that maybe added one layer of complexity. And then you add those two solutions and then keep doing that, potentially adding 2, 3, 4, even 5 or more solutions to create a complex solution to a complex flow problem. So basically, by combining solutions to simpler problems, you could build up solutions to very, very complicated problems. This is how people did a lot of fluid mechanics back before computing was available. So you would use phi to find the velocity field, because once you have phi, you can just take its gradient to get the velocity field. And then you had to find, but let's say you wanted to find lift or something, so then you needed to find pressure. So how do you suppose you found pressure? Well, remember, this is now an inviscid flow, and it's incompressible. So in viscid flows, we can use the Bernoulli equation. So we could also use to find pressures. So what people would do is they would build up complicated solutions to the Laplace equation to develop realistic looking flows for objects. And then once they had the velocity field, they could use the Bernoulli equation to find pressures. So that was a pretty classic way to solve problems for a very long time in fluid mechanics. As I say, it's not used as much now. Honestly, it's easier just to go to the computer. You could even solve the potential flow problem with a computer pretty easily. That's really easy, actually. But you can also just solve the real equations that include the viscosity. But at any rate, it was an interesting technique, and people still talk about potential flow, and they expect you to understand when you can use potential flow theory. So you can use it if it's inviscid, irrotational, and incompressible. And in that case, you can use this Laplace equation to develop flow profiles.